Hi, I'm Rebecca, and today I'm going to help you solve a problem involving a convex mirror. So this is what you're given. An object is placed 10 centimeters from a convex mirror with a focal length of -5 centimeters. Draw the ray diagram below and describe the image. Using the fundamental lens equation, find the location of the image and the magnification. Okay. So to solve this problem, first we're going to need to look at some background theory on mirrors. So let's identify the basic parts of the diagram. The arrow is our object, and we know it is 10 centimeters from the mirror, which is shaped as a section of a hollow sphere with a reflective surface. The mirror is convex because the edges curve away from the observer. The dotted line is the principal axis, the line going through the geometric center of the mirror and perpendicular to the surface of the mirror. Light rays that are parallel to the principal axis converge at the focal point. The length from the mirror to the focal point is the focal length, which in this case is -5 centimeters. The focal length is negative because it's behind the mirror. C is the geometric center, and the distance from C to the mirror is the radius of curvature, which is twice the focal length. To draw the ray diagram, we'll need to start at the top of the arrow and draw two rays. One will be a ray to the surface, as if you were going to go through the focal point. So line up your ruler with the top of the arrow and the focal point, and draw the ray from the top of the arrow to the mirror. Now reflect it back parallel to the principal axis. So start where you ended, and draw a ray parallel to the principal axis that goes back towards your object. The second ray needs to be parallel to the principal axis and reflected back in line with the focal point. So start at the top of the arrow and draw a line parallel to the principal axis until you hit the mirror. Then line up that point and the focal point with your ruler and draw that ray going back in front of the mirror. Now extend the reflected rays behind the mirror. Use dotted lines to show the rays have been extended. From the principal axis to where your extended rays intersect is your image, which is represented by an arrow. Now we can describe the image using our ray diagram. We need to figure out three things. First, is the image real or virtual? The image formed is virtual because the reflected rays didn't converge. We had to extend them behind the mirror. Next, is the image upright or inverted? Our image is upright because it has the same orientation as the object. Lastly, is the image reduced, enlarged, or the same size as the object? The image is reduced. The next task is to find the location of the image, which we can do using the mirror equation 1/do plus 1/di equals 1/f, where do is the distance to the object, di is the distance to the image, and f is the focal length. We know from the problem do equals 10 centimeters and f equals -5 centimeters, and we are looking for di. So we plug in 10 for do and -5 for f in the mirror equation, and we get 1/-5 equals 1/10 plus 1/di. Subtract 1/10 from both sides, and you get -0.3 equals 1/di. You can just switch -0.3 and di to get di equals 1/-0.3, which is -3.333 centimeters. There is no specific unit you use. Because we were given centimeters in the problem, we'll use centimeters. The last part of the problem requires you to find the magnification. The formula for magnification is m equals hi/ho, or m equals -di/do. Since we have di and do, we'll use m equals -di/do. Using m equals -di/do, plug in -3.333 for di and 10 for do. Since the negatives on the top cancel each other out, you're left with m equals 3.333/10, which equals 1/3. Magnification has no unit. Now that you found di and m, you can check your description of your image. Since di is negative, the image is virtual. The image is upright since m is positive, and reduced since m is less than 1. So from the ray diagram, you know that an object placed 10 centimeters from a convex mirror with a focal length of -5 centimeters will produce a reduced, upright virtual image. Furthermore, from using the mirror's equation, you know the image is located 3.333 centimeters behind the mirror, and it is 1/3 times the size of the object.